Welcome everyone to this week's edition of HoloTube, and I think Happy New Year. From my side, I am very happy to have Alberto Nicolis today, and he's telling us about, as you can read from the slide that you hopefully see on the screen, apparent fine-tunings from broken spacetime symmetries. So Alberto, the screen is yours. Take it away.
Thank you very much for the invitation. It's a pleasure to speak here. I will tell you about a paper I wrote a little over a year ago with Ira Rothstein at Carnegie Mellon. And it is also related somewhat to other papers I wrote in the past with my former students and postdocs. But I will not have time to mention much about these two papers. Perhaps in the conclusion, I will mention something if I have time. But what I want to show you is that assuming you're interested in fine-tuning problems in fundamental physics, like the hierarchy problem and the cosmological constant problem, when you consider systems that break space-time symmetries, which is all systems that we know of in everyday life, like solids and fluids, for instance, then there are certain apparent fine-tunings that arise for free, naturally. And by naturally, I mean really in nature, okay, without us having to do anything. And so I find it interesting to ponder why that's the case and what is the role of space-time symmetries, the broken space-time symmetry, if they have an important role, and whether we can learn something by studying these systems regarding the more fundamental hierarchy problems we have in fundamental physics, so in particle physics and gravity. So let me just, Let me just spend one slide talking about the hierarchy problems in particle physics and gravity. I will not go into details also because everybody has a different opinion about them. So if we start talking about them, we never stop. By the way, I should say, whenever something is not clear or whenever you want to make a comment, please interrupt me, okay? If we can, let's keep this interactive so it's more fun for everybody. So what are the naturalness problems that we have in particle physics and gravity? Well, the first is the electroweak hierarchy problem, which can be phrased as why is the weak scale, here parameterized by the mass of the Higgs, why is the mass of the Higgs so much smaller than more fundamental scales? What kind of more fundamental scales are we talking about? Could be a GUT scale, could be the Planck scale. In fact, the fact that the Higgs mass is so much smaller than these scales prompted much model building to figure out what could be a UV completion of the standard model at scales that are not parametrically larger than the weak scale, for instance, supersymmetry. There's no sign of new physics at the LHC, and so we are still facing this question. Why is the Higgs scale so small in a sense? And there is no apparent symmetry reasons in the standard model or in physics, let's say in standard model interpreted as an effective theory that hint at why this could be the case, even though experimentally it's the case. And then a related one, which is even more striking, is the cosmological constant problem. The fact that from cosmological observations, we know that the cosmological constant, and in particular the expectation value of the stress energy tensor, is the stress energy tensor decouples to gravity is very much smaller than any particle physics scale. In particular, is much smaller than, let's say, TV to the fourth. I'm being conservative here. I'm saying that we know that quantum field theory describes the world at least up to energies of order TV to the fourth. A rough estimate of the vacuum energy gives us an energy density of order TV to the fourth. And with no cancellations up to that scale. There's no cancellations up to the scale. So the question is why the value that we observe for the vacuum energy is so much smaller than its natural value. And these hierarchies, so the smallness of the Higgs mass and the smallness of the cosmological constant, are not enforced, as far as we can tell, by any symmetry-based selection rule. There is no approximate symmetry or exact symmetry that tells us that they have to be 0 or small. And so this, for many people working in fundamental physics, is a problem. For others, it's not. They question whether this is really a problem. For some, it's a matter of definition. I don't want to enter the debate because it will take us forever to settle, and probably we will not settle. So I just want to take these as facts, okay, that for some people, these are problems. And in this talk, I want to motivate this claim, that the claim that I write here, that hierarchies like this can happen naturally. And by naturally, I mean in nature, in systems that are undisturbed or not tuned by humans, can happen naturally when we have systems that break space-time symmetries. And I'm not making a general statement here. I'm not saying whenever you break a space-time symmetry, these things happen. I'm just saying that there are examples that I want to talk about in which these things do happen naturally. And it's interesting to understand in quantum field theory, or I will do classical field theory here, how they happen. And the proof of the claim will be, again, just examples. I'm not making any general statements here, but I will show you some examples of real systems, systems that we deal with every day, every minute probably of our lives. So here's my experimental data. If you take any solid, like, I don't know, this phone, and you apply some pressure, you compress it, the stress tensor inside, if you neglect for the moment boundary effects like surface tension effects, the stress tensor inside relaxes to an expectation value that is the pressure that you apply from the outside times delta Ij. And when you release the pressure, so if you now do not press anymore, the stress tensor inside relaxes to 0. Again, up to surface tension effects. And this 0 is not enforced by any symmetry. This delta Ij is enforced by, let's say, isotropy. If you assume that you're dealing with an isotropic solid and you apply only isotropic, only a pressure, let's say, and not some shear at the boundary. But this 0, when you relax the pressure, is not enforced by any symmetry. And perhaps an even more striking effect is this. If you take a bar, okay, either with 2 free ends or only 1 free end, and let's say you anchor it somewhere in a wall. So as long as at least one of the boundary conditions is free, and you look at oscillations, you discover that the frequency of oscillations goes like the wave number square. So in particular, it's the proportional to the inverse of the length square. As opposed to a string, which has exactly the same symmetries, but what do I mean by bar or beam or rod versus string? By string, we usually mean something with a tension, for instance, a guitar string. Okay, a guitar string, if I put a tension, I know just from standard, this is physics mechanics 101, or the free oscillations of a string with a tension, the frequency goes like the square root of the tension times the wave number. And you see here that when you relax the tension to 0, which is equivalent to leaving one of the boundary, at least one of the boundaries free, when you relax the tension to 0, this coefficient goes to 0. And in the language of effective theory, then you're dominated by higher derivative effects. In particular, you get a frequency of order k square. Again, the vanishing of this coefficient is not enforced by any symmetry. It's just your choice of letting boundary conditions free. As soon as you let boundary conditions free, the system relaxes to a state of 0 tension, and this coefficient goes away, and you're dominated by higher derivative effects. This is nothing new, okay? This was well known by Euler, Bernoulli, and I have to thank Ben Frey-Vogel to rediscovering this. So I didn't know about this, but so let me just tell you how I started thinking, how Ira and I started thinking about all these projects. So Ben Freivogel and his siblings are all they're all musicians, and in particular his siblings have perfect pitch. And Ben Freivogel was trying to build a set of tubular bells by just cutting pipes, and he was thinking, as we would normally, we all would, I think, that the frequency of the resonant frequency of a tubular bell would go like the inverse of the length. So he cut all these tubular bells according to this rule, and then he started playing them, and everything was off. And so he asked his siblings to figure out what notes he was playing, and then he did fit them, and he found this dispersion relation. And so he told me about this, and we started thinking about this. And in the end, it turns out that this is very well known. As soon as one of the boundary conditions is free, the frequency does not go like 1 over the length, but it goes like 1 over the length square. So these are obvious. Sorry, this is not obvious, but it's well known. This thing, we are used to it, but we never think about it. The fact that if for a solid we don't exert any pressure, the solid relaxes to a state of zero stresses inside. These things follow from Newtonian mechanics, and so they're not particularly deep, perhaps. But the question is, since they are neither of them, this zero is not enforced by symmetry, and this zero, when the tension goes to zero, this zero is not enforced by symmetry. The question is, how do we understand them in field theory or effective field theory terms, and can our understanding of these things in field theory terms shed some light on more fundamental hierarchy problems? So this is what my talk will be about. So let's start with the solid case. So first we want to describe the bulk dynamic of a solid, and then we want to understand how to take into account the fact that there is a boundary, and at the boundary we can either exert some pressure or let the boundary free. Okay, so how do we do this in field theory? So to describe the mechanical degrees of freedom of a solid, and by mechanical degrees of freedom of a solid, I mean those that are associated with the geometry of the deformations of a solid, I want to think about the solid, for simplicity, as a continuous medium that lives in space and moves in time. And I want to erect a system of coordinates that I call phi1, phi2, and phi3 that lives inside the solid and moves with the solid and gets deformed with the solid if the solid gets deformed. So these coordinates are frozen into the solid, and they just follow each individual volume element. Okay, so these are co-moving coordinates. They move with the volume elements of the solid. So that's why I'm denoting them here as curved axes here, because I'm thinking of a solid that is being deformed. And then I have my lab rigid reference frame. Okay, and so I can think of the mechanical degrees of freedom of a solid as simply the mapping between this space and this space. So these coordinates and these coordinates as a function of time. So this is very much like what we do in string theory when we think about the embedding coordinates as functions of sigma and tau, of worldsheet coordinates. Here I want to do the opposite, since both spaces, if I, at fixed time, let's forget for a second about time, at fixed time, both spaces are three-dimensional. Then I want to talk about the co-moving coordinates as functions of the physical coordinates. So phi I, where I goes to 1, 2, and 3, as a function of x, and then of time when I let the system evolve. And why is this convenient? Because these are just three scalar fields. They do not transform under space-time symmetries. They are internal coordinates of the solid. And they're functions of x and t, and x and t transform nicely, or in the usual ways, under space-time symmetries. In particular, if I want to do everything relativistic, this is just x mu. So now I have three scalar fields as functions of x mu. So I know how they transform under Poincaré symmetries, and I have to ask whether they also enjoy internal symmetries. And to figure out the internal symmetries acting on these fields, I want to think about the ground state. For simplicity, I'm considering ground states in which the solid is only either compressed or dilated, but it's never sheared. This is just for simplicity. Okay, you could redo the same analysis for general shear or even boosted ground states. But if I now consider just an isotropic ground state in which the solid is just either compressed or dilated, then a good choice of internal coordinates is a set of internal coordinates that is perfectly aligned with the physical coordinates. So on the ground state, I want the phi i's to be the same as the xi's up to a proportionality constant that takes into account the level of compression or dilation. And now we can figure out the symmetries by looking at what this ground state looks like and what we would like it to be corresponding to. So in particular, this ground state clearly breaks Poincaré symmetries. Okay. And in particular, it breaks boosts, which it's fine because we want the solid to have a rest frame. So it has a preferred reference frame. So it has to break, the ground state of a solid does break boost physically. But then it also breaks translations and rotations because the right-hand side transforms as x under translations and rotations, but the phi i's are supposed to be scalar fields, okay? So on the other hand, we would like a solid to, at least at very long distances, when we can neglect, let's say, the interparticle separation, to be homogeneous, to be invariant under translation. So physical quantities like, I don't know, the stress energy tensor, for instance, should have an expectation value that at long distances is invariant under translations. And similarly, for simplicity, if we consider a solid with some internal rotational group of symmetries, so in particular, I don't know, a cubic solid, a solid with a cubic lattice, so that there is a discrete subgroup of rotations that leaves the solid invariant, then we would like this ground state to also be invariant under that. But the right-hand side breaks that too. So the way we take this, we solve some of this tension in effective theory is to postulate that there are internal symmetries acting on the scalars that mimic translations. So we have shift symmetries acting on the scalars and mimic the unbroken subgroup of rotations that we want to preserve. So we impose that the unbroken subgroup of rotations acts linearly as an internal symmetry on the phi I. If we impose these symmetries, then these expectation values break the spatial symmetries I told you about, and it also breaks these internal symmetries, but it leaves a linear combination of spatial translations and shifts unbroken. If I shift x and I shift phi at the same time, this ground state is invariant. These expectation values are invariant. If I rotate x by the unbroken subgroup and I rotate phi by the same element of that subgroup, this expectation value is also invariant. So we have to postulate, if we want to reproduce the physics of approximately homogeneous solids with a certain symmetry, rotational symmetry group, we have to postulate these symmetries at the level of the scalar fields. Once we do that, writing down the action is very easy because to lowest ordering derivatives, since we have shift invariance on phi, we have to use derivatives, at least one derivative per field. And for Lorentz invariance, we have to contract these derivatives because we only have scalar fields. So now we are left with two free indices, I and j. And we can write down an action that is a function of this quantity, bij, that is invariant under H. Okay, so we want these indices ij now to transform under this subgroup of rotations, and we want this function that we choose to be invariant under that symmetry. And different symmetry groups, there's cubic and the other groups of solids, of crystals, will have different invariants. For simplicity, I will only focus on isotropic solids, which of course is in idealization. There is no crystal that is isotropic, but if we have crystals made of small domains that are sort of randomly arranged in terms of their orientation, at very long distances, you recover isotropy. So for simplicity, I will replace this discrete subgroup of rotations with the full SO3. This is just to simplify the algebra, and also because many solids and long distances behave like this. But if one wants to, one could repeat my analysis for discrete subgroups. So this G is an arbitrary function that must be invariant under this group of rotations that I chose. And in particular, if I choose SO3, this must be a rotational invariant function of Bij. So it has to involve traces, determinants, and stuff like that. Okay, when we don't need to specify for now which invariants we're going to use. So once, plus of course, in effective theory, we're going to have higher derivatives, okay? And they will not play a role in my talk, so I will neglect them, but this can be organized as a derivative expansion, I call effective theories. And now we discuss the physics of small perturbations. In particular, small deformations of a solid can be thought of as the classical fields associated with the phonons, or the phonons can be thought as the quanta associated with deformations of a solid. So we take our background, which was alpha xi, where alpha for now is a parameter. We will see later what fixes it. And we deform it by adding 3 perturbation fields, pi I. Okay, so at least for small deformations, the more general phi I can be thought of as this xi plus pi I. And then we take the action and we expand it to quadratic order in pi. And we discover that at quadratic order, not surprisingly, there's a kinetic energy for my phonon fields. And there are 2 independent gradient energies, one for longitudinal perturbations, so divergence of pi, and one for transverse perturbation, the curl of pi. And they come with different propagating speeds, which I call CL and CT. These at this level can be thought as free parameters. If I want to interpret them at the level of G, they just correspond to specific derivatives of G with respect to its argument, evaluated on the background. Okay, but for now I can take them as free parameters. Okay, and now this is the bulk description of a solid. Now for isotropic solids. Now, how do we talk about a boundary? So as we said in my original slide, I wanted to talk about the possibility of having some pressure acting on the solid or leaving the boundary conditions for the boundary of the solid free. So I need to talk about the boundary of a solid. So going back to this picture of comoving coordinates versus physical coordinates, the boundary is fixed in comoving coordinates. Let's say in this plot here, it is a cube that goes from 0 to 1, 0 to 1, and 0 to 1 in all directions. But in comoving coordinates, in physical coordinates, the boundary can move. Okay. So let's look at a two-dimensional solid, which is a little simpler to visualize. So I have my comoving space parameterized by phi1 and phi2, and I have my physical space x1 and x2. And I draw a surface in comoving space, and that corresponds to the boundary of my solid. In this case, looks like a potato, let's say, okay? And this is fixed once and for all in comoving space. In physical space, I can take my potato, and if I'm strong enough, I can compress it a little bit, or dilate it, or even shear it, okay? So the boundary will move and will get deformed in physical space under stresses or under time evolution, but it will stay fixed in comoving space. So in comoving space, I can parameterize the boundary with a function f, function of my fields, that is, let's say, 0 on the boundary, and then it's bigger than 0 inside. And so I can parameterize my solid with a theta function. The volume of the solid corresponds to the theta of f. It is non-zero inside and 0 on the boundary, and negative outside. I didn't write the negative part here. Okay. So the most convenient way to, in this language, to talk about a solid with a boundary is to multiply the action that I gave you before by a theta function, okay, that tells you when you are inside the solid or not. So the action of the solid is non-zero only inside the solid, and it's zero outside the solid. And you see, everything is easy in this language because these are scalar fields. So a theta of a function of a scalar field is still a scalar. So I can just multiply my Lagrangian density by a scalar. I still get a scalar Lagrangian density. I'm integrating in d4x. By the way, I'm doing everything without gravity. Gravity can be introduced in the usual way. These are just scalar fields. So introducing gravity is very easy. And so if I don't add now any external sources, this is a solid with a free boundary. There is no forces in this action acting on the solid, apart from the internal forces coming from the formations if the solid starts off in a deformed, let's say, state. So this, I claim, is the action for a solid with a free boundary. The equations of motion can be derived in the usual way, and they also correspond to the conservation of the stress energy tensor, or to the conservation of currents, because you remember we have shift symmetries acting on phi, so we have conserved currents. So these are the equations of motion that come from varying the action with respect to phi. Phi is in here. And now I want to look at these equations of motion. So when I act with derivatives on this on the thing inside, okay, I have a term in which the derivatives acts on the theta function, and this gives me a delta function times other stuff because the theta has a non-trivial argument, but it gives me a delta function that is a delta of f of phi, so it's only active at the boundary. So this will give me a boundary equation of motion. And then it gives me, when the derivative acts on everything else, it gives me a theta function times the derivative acting on everything else. So these are the bulk equations of motion that I had in the absence of the theta function, but now multiplied by a theta function. So I have a bulk equation of motion that corresponds to the conservation of the stress energy tensor inside the solid. And if I'm looking for static solutions, this turns out to be equivalent to saying that the stresses have to be constant inside the solid for static solutions. And one can check very easily that any configuration of this form, so linear in X, a configuration in which the fields are linear in X, with any coefficient, obeys this equation. This is just saying that regardless of the external stresses that we impose on a solid, inside the solid, for static solutions, the stresses have to be constant, because if there is a gradient of stresses, there is a force on a volume element, and so the solution is not static. So for static solutions inside the solid, the stresses are constant, regardless of the proportionality constant, regardless of how compressed or dilated the solid is. But at the boundary, if you go through the derivation, you discover that at the boundary you have that the components of stress is normal to the boundary, and here is the normal vector in physical space, normal to the boundary. So the normal stresses have to be zero, okay? However, now if I combine these two equations, so the Tij inside the solid has to be constant, and then the normal stresses have to be zero at any point on the boundary. But by going around the boundary, the normal goes around the solid angle completely. So it turns out that this equation combined with this equation tells me that the stress tensor has to be zero everywhere inside the solid. And this, you see, is not enforced by any symmetry, this zero, because it comes from the fact that I have a boundary, and it's a free boundary, so I also have an equation of motion at the boundary. In the absence of the equation of motion at the boundary, I don't get zero. Or if the equation of motion at the boundary is different, because, for instance, if I'm pressing on the boundary, then I don't get zero. So it's not enforced by any symmetry. You see, the boundary itself can be highly non-symmetric, can be any potato shape you can imagine. You still get zero. This, by the way, this zero fixes alpha, in the sense that this should be interpreted, since the Tij that I have inside the solid depends on alpha, depends on the level of compression or dilation. When I relax the external pressure and I let the boundary free, the stress energy tensor will relax to 0 because the solid itself will either expand a little bit or compress a little bit and find the sweet spot of alpha where the stress is 0. This can be understood better by thinking about it in terms of an effective potential. I can go back to my action, plug in these ansatz, the fact that the fields are static and depend linearly on x. I just plug it in, okay? And so here now I get a theta with the function of alpha x. So now it's a theta in physical space. So it bounds the boundary if you want. And then, sorry, bounds the solid in physical space. And then I get g of bij. Bij had to do with derivatives of phi. So the derivatives of phi on a solution that is linear in x are constant and they are proportional to alpha. And so I get a function of alpha here, g of alpha, suitably defined. Okay. And if you look at the fact that there is a non-trivial Jacobian between physical space and comoving space, because I have phi equals alpha x, so I have an alpha cube determinant of a Jacobian. Overall, you get an effective potential for alpha, for the level of compression, that is the comoving volume in comoving space, so that's fixed, it's a constant, it does not depend on alpha, times this particular function of alpha. And when you look for the minimum, you find that this is equivalent to setting Tij equal to 0, not surprisingly, and it's equivalent to this differential equation. Sorry, it's not a differential equation. It should not be interpreted as an equation for G. G is given once and for all once you give me the equation of state of the solid, once you tell me how the solid responds to external stresses and stuff. So G is given once and for all. This is an equation that fixes the value of alpha. It's equivalent to minimizing a potential. You're really minimizing the effective potential. And so let's call the alpha bar the value that minimizes the potential. So the solid relaxes to the minimum of this effective potential, and the minimum of this effective potential happens to have a vanishing expectation value for Tij. Now, if you look, now you can ask, okay, when the solid relaxes to this sweet spot, is the phonon effective theory constrained in some way? Do certain coefficients vanish at this sweet spot? And if they do, this could be seen as a fine-tuning, but arising naturally, meaning that if there was no symmetries enforcing these fine-tunings, this could be some sort of model, if you want, for an hierarchy problem. So it so happens that for a three-dimensional or two-dimensional solid, there's not much associated with this vanishing of Tij at the level of phonons. So if I look again at phonons, I expand my fields in terms of coordinates plus phonons, and I look at the expansion of my building block for the effective action, which is Bij. I plug it in. Remember that theta was the theta was a function of f of phi. So now I also expand the f inside the theta as a function of the phonons. And then I expand the g as a function of the phonons. So you put everything together. When I look at the expansion of the theta, I'm going to have some delta functions, etc. And so it so happens that once you reorganize things in the effective action, you discover that the relaxation condition, Tij equal to 0, does not really have strong constraints on the phonon Lagrangian. In particular, in the bulk, you get exactly the same Lagrangian as before. Not surprisingly, because the bulk somehow, you could take the boundary to infinity, the physics of the bulk is pretty much the same. But at the boundary, you get a very specific boundary action. You get this boundary action. You got the phonon field cross the curl of the phonon field. And the coefficient in front is completely determined. And this boundary action is not enforced by any symmetry, meaning it's compatible with the symmetries for sure, but the fact that it takes this very specific form is a consequence of Tij equal to 0. It's not immediate to us what this means physically, meaning what kind of physics at the boundary does this correspond to. Probably it does mean something. Let's say if I look at waves that deform the boundary, if I ping the boundary and look at how waves propagate, probably does mean something, but it's not immediately obvious. So what is much more obvious is when we go to the limit of the one-dimensional bar. So now you take the three-dimensional solid and instead you consider it very elongated in one direction, okay? And let me first describe directly the dimensionally reduced effective theory, so directly the one-dimensional effective theory for the bar, and then I will tell you how to get there from dimensional reduction from 3 plus 1 dimension to 1 plus 1 dimension. So let me think about a bar. How do we describe a bar with what we know about solids? Well, what is a bar in this language? It's a 1 plus 1 dimensional solid embedded in a 3 plus 1 dimensional space. So it's like string theory, more or less. But of course, it's string theory not made of fundamental strings that have all sorts of symmetries. It's string theory made of a solid, okay? How do we do this? Well, in this language, we do this by saying that the degrees of freedom are the embedding coordinates. So these are purely geometrical objects. These tell you the shape of the bar in physical space-time as a function of the worldsheet coordinates, sigma and tau. But there's also another degree of freedom, which is the degree of freedom that describes the fact that this bar is made of a solid. So before, we needed 3 scalar fields to describe a three-dimensional solid. Now we are dealing with a one-dimensional solid, so we need a one worldsheet scalar, which is a function of sigma and tau. Okay, so this is the solid comoving coordinate on the worldsheet as a function of the worldsheet coordinates. And now, how do I describe the physics of a bar with one free end? I do exactly what I did before, but in 1 plus 1 dimensions, taking also into account the fact that I have the embedding coordinates. So how do I do it? Well, I do an integral over the worldsheet coordinates. Sorry, here there's a typo. It should be d tau d sigma, not d tau d tau. This one is sigma. So I have a worldsheet integral of the square root of the determinant of the induced metric, and the induced metric comes from the embedding coordinates. So this is the invariant measure on the worldsheet. And then I have my G of B, so my solid action, my solid Lagrange, but now my B, first of all, I only have one field, so it's not a matrix anymore. So I have d phi, d phi. Contracted not with eta like I was doing before, but here I'm doing everything on a curved space time, which is the worldsheet. And so I have to use the induced metric to contract these indices. And then to talk about the fact that the bar ends at one point and that point is free, like I was doing before, I used the theta function. Here, the theta function is very similar. Before I had to use the fact that I had a function in comoving space defining the boundary of my solid. Now I simply have phi itself because I already have one comoving coordinate. So phi should be bigger than some phi star that corresponds to the end. Okay, this is easier than what we did before. The induced metric, of course, is defined in the usual way from the embedding coordinate. And now one can look at the ground state, let's say the bar at rest. Bar at rest, well, first of all, let me choose a convenient gauge for sigma and tau. Of course, I have reparametrization invariants on sigma and tau, so let me choose a gauge for them. The most convenient gauge is that tau should be the physical time at 0, and sigma should be the physical first coordinates, let's call it x1, okay? So this is along x1, and tau is simply time. So this is unitary gauge. Then I have x2 and x3, so the transverse coordinates to the bar are 0 on the ground state. And my solid field, like before, is some alpha times a compression level, compression or dilation level. Sorry, is alpha, which is the compression or dilation level, times my longitudinal coordinate, sigma. Like before, I can write down an effective potential for alpha that simply comes from taking this action and plugging in the ansatz. And this relaxes like before, if the equation of state is such that there is such a state with zero tension or pressure. It relaxes to an alpha bar with vanishing tension or pressure. T sigma sigma is zero when this effective potential is minimized. Exactly like before. Now we can study perturbations. We can expand the solid field around this background, alpha bar sigma plus perturbations. Let's call them var phi. And we can expand the two transverse coordinates as their expectation value, which was 0 plus pi 2 and pi 3. X0 and X1 are fixed always to be this if we choose unitary gauge also in the presence of perturbation. So let's use unitary gauge. So there's no perturbations in X0 and X1. The gauge is completely fixed and we can read off the Lagrangian. Now, the crucial aspect here is that the dependence of the action when we expand in perturbations on the perturbations of the transverse coordinates, so the dependence on the action on x2 and x3 is very easy to figure out. Why? Because at quadratic order, so first of all, the x mu's only enter the action through the induced metric. And at quadratic order in perturbations, the induced metric takes this form, is the flat metric plus this combination. So to figure out the quadratic dependence on the pi field, it's enough to know the linear dependence on the induced metric. But the linear, so it's enough to know this part of the action. But by definition, what multiplies the linear perturbation of the induced metric is the stress energy tensor on the worksheet. By definition, the variation of the action with respect to the induced metric is the stress energy tensor. So this part, this equality sign, is enforced by symmetries, in the sense that if you want, it's almost by definition that that's the stress energy tensor. And so in particular, the sigma sigma, so the gradient energies of the pi fields will have to do with the sigma sigma entries of the stress energy tensor, like so. But remember, the ground state corresponds to a vanishing spatial stress tensor, vanishing tension or pressure. So this is 0. So this tells you this is a 21st century, if you want, way to rediscover this thing that has been known by humans since forever ago, that a bar with one free end does not have a gradient energy for small oscillations at this order in derivatives. It only appears at higher order in derivatives. And there is a part of this argument that is enforced by symmetry, this equal sign here, that relates the dependence of the phonon fields to the stress tensor. And there is a part, this equal sign here, that is not enforced by symmetries, that sets this to 0. This is enforced by the relaxation of the bar to a ground state with vanishing tension. And so putting everything together, the action for the pi fields is a gradient energy, sorry, it's a kinetic energy. The gradient energy to lowest order in derivatives vanishes because the tension vanishes on the relaxed bar with one free end, and you're dominated by higher derivative corrections, which I didn't write. They have to do with the extrinsic curvature square, the Riemann, the intrinsic curvature, etc. And they give you the lowest non-trivial order is a 2 derivative per field gradient energy. So it's a 4 derivative gradient energy, which gives you a dispersion relation omega squared equals k to the 4th. You can get exactly the same results by thinking about dimensional reduction, like I was mentioning. Suppose you have a solid, let's do for simplicity a 2-dimensional solid that is very long in one direction, let's say even infinite, but it's pretty skinny, so its thickness is much smaller than its length. Let's call the thickness delta. And I consider it relaxed to its state of 0 tension. Okay, so the solid is completely relaxed to a state of 0 tension. And now I look for perturbations of the phi fields. And I can compute these Green's functions for these pi fields that tell you the response of the system to local sources. For simplicity, I will look for the static Green's function and also integrated in Y. So this is essentially the response of the system to static sources that are homogeneous in the transverse direction. Okay. Then you discover that there is some sort of classical RG flow. There is a very striking difference between short wavelengths, shorter than delta, so in which you probe the bulk physics if you want, and very long wavelengths, so the wavelengths longer than delta, in which you don't see the thickness essentially, and this behaves like a one-dimensional system. So for the one components of the Green's functions, one is the longitudinal direction. So for the longitudinal phonons, for the longitudinal perturbations, essentially, the Green's functions goes from what you expect in the bulk, 1 over CL square K square, CL is the longitudinal speed, to when you go to very low wave numbers or very long distances compared to delta, you get pretty much the same with a renormalized C bar L. This is all classical, okay? I'm not doing anything quantum. This is all classical. A renormalized speed of sound, okay, which is a function of the two bulk speeds of sound speeds, the longitudinal and transverse one. However, for the transverse modes, the two components of the Green's functions, if you look at these Green's functions, I'm not displaying the full answer because it's kind of complicated. I'm just displaying the limits because the limits are simple. So for the transverse Green's functions, you go from what you expect in the bulk, 1 over CT square K square. So when you probe very short distances, you don't see somehow the boundary. So you are just probing the bulk physics. So this is what it is. When you go to very long distances compared to delta, K squared disappear and you are left with K to the 4th, exactly like we discovered in the case of the one-dimensional bar, with a coefficient that depends again on delta, because it's a higher derivative correction, so there should be some dimensionful coefficient in front, and a ratio of speeds of sound. Let me just conclude by mentioning something that I've neglected so far, which is surface tension effects. Okay, so whenever we have a boundary or a surface, we know that we can have surface tension. More in general, in the language of effective theory, we know we can have terms in the action that are localized at the boundary, and as long as they are consistent with the symmetries, they should be taken into account using the usual rules of effective theories. Now, we haven't understood yet how to parameterize the most general boundary action compatible with the symmetries yet, in the sense that the symmetries are tricky because the boundary itself breaks a bunch of symmetries. So it's not obvious now what to write. For instance, what people usually write in, let's say, I don't know, biophysics, for instance, you have cells with membranes, etc. So they write simply a boundary action that is proportional to the area of the surface. But that's not obvious why that should be the case, at least if you follow the effective theory principles, because there are, at the same ordering derivatives, there are other terms that look compatible with the symmetries. And so it's not immediately obvious how to proceed. But what we can say for sure is this, that the boundary action should have a delta function localized at the boundary, or at higher orders in derivatives, delta prime, delta double prime, etc. So let's look at the delta. It should be it should be associated with an invariant measure at the boundary. So to make it invariant, you want a derivative of f, so that if you change your definition of f while still keeping the geometry of the boundary the same, this product is invariant. And then there should be a boundary Lagrangian that depends on your fields and their derivatives. And by dimensional analysis, there should be a microscopic length scale that somehow tell you perhaps the thickness of the boundary that you're talking about. There should be a transition happening between inside and outside, and that transition happens over a certain distance, so that's a UV scale. And then everything else is probably of the same order of magnitude as the bulk energy densities, which are of order of, if we consider a non-relativistic solid, for instance, they're of order of the mass density times the typical propagation speeds, like the sound speed square. Okay. But what's crucial is that there is a microscopic UV scale in front. If you want, boundary actions are a higher derivative effect. Okay, compared to here, you see, you go from theta to delta, there's a derivative there. So the derivative, since it has to do with comoving fields, should probably be weighed by a comoving UV scale, but there is still a microscopic scale in front. And so when you look at the equations of motion now, if you include surface tension effects, I call this a surface tension. It's more general than a surface tension, but I call it a surface tension. If I now look at the modified equations of motion, meaning the equation of motion that I had before, plus what comes out of this boundary action, I discover that Tij inside the solid is not zero anymore, but it is of order of the typical energy densities I can expect inside the solid times something of order microscopic scale over macroscopic scale. R is the comoving curvature radius of the solid. For instance, spherical solid, this is exact, you can do the computation exactly, and this is exactly what you get. The coefficient in front of the boundary action, L divided by the radius. So in general, if I think about a solid with some microscopic spacing, little l, and some macroscopic radius of curvature, capital R, this is what I get, L over R, microscopic over macroscopic. So now, this for macroscopic solids is much smaller than the typical energy densities I can expect inside the solid. So Tij is not strictly zero inside any solid like this one, but it's of order of the typical energy density, the energy densities that I expect in a solid like this, times the interparticle separation divided by the size of the object. So it's fantastically small, but it's not exactly zero. So this somehow takes the question of the hierarchy. This takes this moves the question of why there is this hierarchy between Tij and typical energy densities of this solid to a different level. It's like asking, why are solids large? Why is it natural to have huge solids in nature compared to the interparticle separation? It's not obvious to me what the answer is, but the fact is there's plenty of macroscopic solids in the world, and we certainly did not have to fine-tune them. There are mountains or planets that we didn't have to fine-tune, and they exist. So I find it interesting that we can talk about these hierarchies in the language of effective field theory, and they're not immediately obvious. They are I don't know. It's a rephrasing of the question, if you want, and I think it's worth investigating. I think I have to stop, but let me just mention that if you now formally do the same with a time-like field, so here we were talking about space-like fields, now phi I proportional to xi. If you also include a time-like field, which in the language of condensed matter corresponds to, instead of solid, corresponds to having a super solid, you can also formally get the same result for T00. T00 relaxes to 0. Now, however, this requires having, so for solids, we have a boundary in space, and this enforces Tij equal to 0. To enforce T00 equals 0, you need a boundary in time, and it's not obvious what it means that a system has a boundary in time, and in particular, it's not obvious what it means to relax, because you see Tij equals 0 means that with the boundary in space means that if Tij is not 0 as an initial condition, the solid will relax eventually by moving the forming a little bit to make it 0. But if T00 is to be 0 when I meet a boundary in time, it's either that boundary condition is either obeyed or not, and I don't have time to relax so that I can obey it. It's as if it's not obeyed, there's something inconsistent with the theory. So we're still quite confused about how to apply this to time-like scenarios in which we can set T0, 0 to 0. Of course, this would be interesting to talk about the cosmological constant problem in this language, but we're still confused, so I don't have anything particularly interesting to say about this. So let me just conclude by saying that there's plenty of examples of apparent fine-tunings in nature. There is a quantum field theory description of them, and we can sort of understand where they come from. But there are more examples that I didn't have time to talk about. But the question is, what are the generalities? This we still don't know. What is the role of broken spacetime symmetries and why it's important to break spacetime symmetries, if it is important, and whether after we understand the general lesson, whether we can find potential applications of these ideas to the hierarchy problems of fundamental physics. Thank you very much.
Thank you so much, Alberto, for this very interesting talk. Do we have questions? Kevin.
Hello. Hi, Alberto.
Hello.
Sorry, you can hear me good. Thanks. Thanks for the wonderful talk. I was hoping I could try to make an analogy with another system, and then you can tell me if that analogy is fair or not. Particularly with the part of your discussion about solids, where you wrote down a boundary action where the coefficient had to be or first of all, the action had to be some specific thing, curls of something, whatever, and then the coefficient had to be precisely CT squared. Can I make an analogy with gravity in the case of, say, Einstein-Hilbert versus Gibbons-Hawking-York, or the coefficient of Gibbons-Hawking-York has to be precisely twice of the coefficient of Einstein-Hilbert? And the reason why I'm asking is because in that case, of course, we're familiar. First of all, I've never heard of that case being called a naturalness problem, though maybe perhaps it can be. But secondly, in that case, I could have said, well, the Gibbons-Hawking-York form is fixed because I need the Gibbons-Hawking-York variation to precisely cancel the boundary variation of the Einstein-Hilbert one, right? So just in order to have a well-defined variational problem that fixes the form already of Gibbons-Hawking-York, I wouldn't call that a symmetry necessarily. So I don't know. It doesn't really fall under the usual like naturalness problem that I'm familiar with. But does the question make sense? Or a statement?
Yeah, I think it's a very interesting question. I have nothing. I didn't think about it, so I don't have anything relevant to say. Perhaps the difference here is that this case is part of a continuum, in the sense that if I do exert external forces on the solid, these coefficients change. So in the sense that there will be new terms compatible with the symmetries that I have to add here. You can still see my slides, right?
Yes.
Yeah.
Yeah. So there's a new terms that I have to add here, whose coefficient will be proportional to the Tij that I generate with these external forces. So it's a property, if you want, this form of the action for the phonons, it's a property of the state about which I am expanding. If I expand about a different state, for instance, if I have some, I don't know, some time evolution. So if I'm not looking at static configurations, but I have some time evolving state and I expand about that, or if I have static forces that deform my solid in ways that generate a Tij, I will have a different coefficient. So it's not that. Yeah, but it's a good question. I will have to think more about it. I don't know. Mm-hmm. But if you want, is there an analog in your example? Is there an analog of what I'm saying now of externally of changing a little bit things?
If you imagine, say, I can the only thing I can think of is if you imagine a universe in a multiverse, of course, and if there are forces that well, supposedly they're not supposed to be able to communicate with each other. So I'm not sure if one universe is able to exert force on the other, then obviously they can communicate. So yeah, I don't really know what that, you see, if you're going to try to use this argument to say something about cosmological constants, so A, you would need, as you said, time evolution, and then B, you would need to somehow be able to think of what happens at the boundary of the universe. Not sure if, is it the boundary of the universe or just the boundary of the observable universe? Because I'm sure. Anyway, my goal is to, I guess, in the question is to try to figure out how to get closer to the cosmological constant problem.
Yeah.
Bring gravity into the question.
Yeah, that's interesting. I haven't thought about it. I will have to think about it.
Thank you very much.
Thank you.
Yeah, thank you for raising that interesting question, Kevin. Are there other questions? Maybe while others think about this, then I can maybe connect this to holography and ask you if you have thought about boundary conditions on fields in holography and how potentially there are fine tunings in the models that we build out of holographic like construction principles. I mean, just we think about boundary conditions a lot in holography. Just the scalar fields example where you have alternative a window of alternative quantization, and so holography has a lot to do with boundary conditions and is determined very much by boundary conditions. And then just thinking about maybe a subset of them being chosen as in a way that you enforce these relaxation conditions. Would it have implications on how we, like, what properties our holographic models have?
It's interesting. I haven't thought about it, but is there a way? So if I think about the example of the scalar field that you were mentioning, is there a way to not impose boundary conditions, which is equivalent to saying they are free?
It's maybe mentioning the scalar field was not a good idea, but maybe more towards the direction of energy momentum tensor and maybe effective actions and so on. And then I could imagine situations where you consider the boundary energy momentum tensor and like one would do in fluid gravity, for example, and see if there are ground states that have similar properties like the boundary conditions that you pointed out, like tensionless one or shearless ones and so on. Potentially leading to a classification of I don't know, models or states. I haven't thought about it. It just brought, like, this popped into my mind, this question.
So sorry, let me understand your question. Are you saying, suppose that on the CFT side I have a situation like the one I'm describing? What is the question? What does this correspond to in the bulk?
I would probably think about it the other way around. Think about gravity and think about setting boundary conditions on the gravitational fields, and then asking the question, if I think about it in a way, the first thing I thought of was really fluid gravity, where you have part of the equations of motion from gravity describing or involving the boundary energy momentum tensor and boundary conditions. So in a sense that is what I was thinking about, but I haven't thought about it in depth. I just wondered if you had thought about it. That's all.
No, I haven't, but yeah, it's interesting. I don't. Yeah, or maybe a related question. So if suppose I feel part of ADS with a system like this, some sort of ocean or some sort of solid that feels part of ADS, but I leave the boundary of this solid free. What is the corresponding state in the CFT, and what properties does it have? I don't know. I don't.
Yeah, I didn't want to distract from the main topic. So are there, thank you for commenting on it. Are there other questions? Okay, well, that does not seem to be the case. So I will stop the recording here. Thank you again, Alberto. We usually stick around for a minute after the recording ends in case there's any informal questions that somebody would like to ask. And with that, I am looking forward to seeing everyone next week. Thank you again.
Thank you.